welcome. Let us move forward. Now let us look at equilibrium constants. I am sure you know what equilibrium constants are. You must have done this in your 11th standard, 12th standard chemistry, and probably in some other courses in the engineering discipline or in the biotechnology course before you took this course. So you already know what equilibrium constants are. What I am going to give you here is a formalism from the fundamentals to get at equilibrium constants. So you will know where it all rests on, and so it will be much easier for you to have an overall picture in terms of some fundamental thermodynamic quantities. To do that, let us first consider a perfect gas mixture, and as we saw in module 4, especially equation 4.1, the expression for chemical potential of species I in the case of a perfect gas mixture was mu I equals mu I naught plus RT ln Pi, which is the partial pressure of component I in the mixture. If we substitute equation 4.1 in equation 6.14, equation 6.14 is the condition for reaction equilibrium, sum over mu I equals 0. Now we are going to substitute mu I with mu I naught plus RT ln Pi. If we do that, then we could write sum over mu I into mu I naught plus RT ln Pi equals 0. This is this condition here, which can of course be written as, we are just multiplying the terms and combining them appropriately using the definitions of log and the definitions of log of a to the power b and so on. We are going to do that now. So if you do that, sum over I mu I naught plus RT is a constant here, T is a constant here, sum over I ln of Pi power nu I. If you recall, this would have been nu I ln Pi, which is ln of Pi power nu I. You can work this out by looking at the properties of the log function, and this is summed over all I, this equals 0. Or you can write this as nu I mu I naught sum over I equals minus RT, this is sum of log, which is nothing but log of the product that we all know, product of, as represented by this big pi here, product of Pi power nu I. Let us call this equation 6.16, and let us define this particular quantity, product over I Pi power nu I, the stoichiometric coefficient, the partial pressure time raised to the power of the stoichiometric coefficient for each of the species involved as Kp. You would recall Kp, the equilibrium constant with respect to partial pressure, that essentially comes from this. So product over I Pi power nu I is defined as Kp, equation 6.17, and therefore we can write 6.16 as minus RT ln Kp equals sum over I nu I mu I naught. Therefore we have a means of getting Kp in terms of the mu I naught values, the standard chemical potentials of I species multiplied by the appropriate stoichiometric constants and summed over all I would lead to minus RT ln Kp. Let us call this equation 6.18, and to illustrate the above, to get it in into familiar territory, since we are familiar with equilibrium constants from earlier courses, let us consider the reaction mixture given by equation 6.1, which is 2A plus B giving you 3C. Let us consider that for a minute to be a perfect gas mixture. In such a case, this is the equation 6.18 for this particular reaction can be written as minus RT ln Kp. What is ln Kp? ln of the product of Pi par nu I. You know that nu I is positive for the products and negative for the reactants, and therefore if you multiply that all together, it will be Pc cubed into Pa to the power of minus 2 into Pb to the power of minus 1, which can be written as Pc cubed divided by Pa squared Pb, and of course the ln comes from here. This equals 3 mu c naught minus 2 mu a naught sum over I mu I naught, 3 mu c naught minus 2 mu a naught minus mu b naught. We will call this equation 619. Therefore, this must be very familiar to you in terms of the equilibrium constant. How do you find that if given the partial pressures is like this, and you can relate it to the standard chemical potentials for that particular reaction. Let us stay with the perfect gas mixture for a little while longer, and as you can recall, there are many other equilibrium constants. The earlier one was based on partial pressure. You could have an equilibrium constant based on concentration, based on mole fraction, and so on, and they can be arrived at as follows. For the ith component, the partial pressure can be written as Ni by V RT. This is from the ideal gas equation, perfect gas mixture, so mixture of ideal gases and so on. So Ni by V RT is partial pressure, which Ni by V can be is nothing but the definition of the concentration, the molar concentration. Therefore, Ci RT, let us call this equation 620 for in this context, and if we substitute equation 620 in equation 617, that will become very clear right now, and transposing, we will get Kp equals pi into Ci RT the whole power nu I. Can you do this bit of algebra right now? Just substitute 620 in 617 and get this expression. Take about 5 minutes to do that, and which can further be written as this. This is just the algebra part, the log and raising it to powers and so on. You need to get comfortable with this, so I will give you about 5 minutes to do this. Go ahead please. Okay, you should have arrived at Kp equals product over I Ci RT the whole power nu I, which can of course be written as RT to the power of sum over nu I times the product of Ci power nu I. Let us call this equation 621. This is the definition of Kp, and if we call this as Kc, product over I Ci par nu I as Kc, then it is easy to see that Kc is nothing but Kp into RT raised to the power of minus sum over all the stoichiometric constants nu I. Let us call this equation 623. Just not this, there is probably one more. Let us recognize that Pi is nothing but P into Yi, equation 624, and let me leave you with this for another 10 minutes to derive Ky, the equilibrium constant based on the mole fractions Yi. Can you go ahead and do it on the same lines as we did for this? I will present the results after 10 minutes. Go ahead please. Okay. Now taking Pi equals the total pressure times the mole fraction Yi, and if we follow a similar exercise as above, write Kc in terms of, or Ky in terms of Kc and so on, you should get Ky is nothing but Kp into P raised to the power of minus sum over all nu I. Hopefully you got this in your own exercise, where our Kp is defined, or sorry, Ky is defined as product over I Yi, the mole fraction, raised to the power of nu I, the stoichiometric coefficient. Let us call that equation 626. Now all those equations that we derived so far, the equilibrium constants, were applicable for perfect gas mixtures. If the gas mixture is imperfect, which is usually the case, then the only change that we need to make, since we are working in terms of chemical potentials, is that the chemical potential needs to be expressed in terms of fugacities instead of partial pressures. This was given in equation 4.2, chemical potential in terms of fugacities mu I equals mu I naught plus RT ln Fi hat. So replace fugacities wherever there were partial pressures earlier, and if we do a similar exercise, I would leave this for you to do as a homework. So if you do a similar exercise as for Kp, we should get minus RT ln Kf. Kf is the equilibrium constant based on fugacities, as equal to sum over I nu I mu I naught, where Kf, the equilibrium constant based on fugacity, is defined as product over I Fi hat raised to the power of nu I, that is our Kf. Let us call that equation 628. When we are almost out of time, when we meet in the next class, we will take things further. See you there.